What if I told you that 3 times more water than all our oceans combined is locked deep inside Earth's solid mantle?
But don't picture underwater caves or subterranean seas. This water is, and it's not liquid, chemically trapped inside solid blue rock.
Hundreds of miles beneath our feet lies a rare, microscopic mineral called ringwoodite, acting like a giant geological sponge. For decades, geologists argued whether this hidden ocean was real, until an extraordinary diamond surfaced from the deep.
Today, we dive 400 miles beneath the surface to explore how this subterranean water keeps our entire planet alive.
Get ready to rethink everything you know about Earth's geology. Let's dive in.
To find ringwoodite, you have to travel down into the mantle transition zone, 400 miles below ground.
At these extreme depths, the pressure is over 100,000 times greater than the air at sea level.
Surface minerals like olivine cannot survive here. The pressure squeezes their atomic structure into entirely new forms.
First, the mineral turns into wadsleyite, and under even higher pressure, it transforms directly into ringwoodite.
In this environment, temperatures exceed 2,000 degrees Fahrenheit, yet the rock remains solid due to the crushing weight above.
This extreme layer acts as a massive barrier between Earth's upper and lower mantle.
But how exactly can a solid, heavy rock hold water without dripping?
It all comes down to atomic defects. Ringwoodite doesn't store water as liquid droplets in cracks or pockets.
Ringwoodite can absorb up to 1.5% of its total weight as bound water molecules.
1.5% might sound small, but when you multiply that by thousands of miles of mantle rock,
the sheer volume equals the water weight of every ocean on surface Earth, multiplied by 3. For decades, water-bearing ringwoodite was just a theoretical prediction. It was created only in physics labs.
scientists could synthesize ringwoodite, but they had zero physical proof that it actually existed naturally inside Earth.
That changed in 2014, when geologists examined a tiny, scarred diamond unearthed in Juina, Brazil.
This diamond didn't form near the surface like most gems. It was blasted up from over 400 miles deep by an ancient volcano. Trapped deep inside the diamond was a microscopic specks of mineral, sealed off from the outside world for millions of years.
Infrared testing confirmed it. The inclusion was natural ringwoodite, and it was full of water.
But one microscopic sample wasn't enough to prove an entire underground ocean existed.
Researchers turned to seismology, listening to sound waves generated by thousands of earthquakes, echoing through Earth's interior.
Seismic waves speed up through cold, dry rock, but slow down significantly when they hit damp, slushy mineral zones. Using the US Array, a massive network of over 2,000 seismic stations, geophysicists mapped the transition zone under North America. The data showed massive areas where rock was actively melting as it sank, releasing trapped water into the lower mantle.
The seismic maps matched the diamond discovery perfectly. The deep ocean was real.
This discovery forces us to answer one of science's biggest questions. Where did Earth actually get its water? For decades, the leading theory was comet impacts, icy asteroids bombarding early Earth millions of years after its formation. But if the deep mantle holds 3 times our surface ocean water, comets couldn't possibly account for all of it.
Instead, Earth may have absorbed water directly from the dust cloud during its original planetary birth 4 billion years ago. Our planet didn't import its oceans from space. It brought them along from the very beginning, storing them deep inside of rock. Ringwoodite preserved Earth's water inside a massive planetary vault.
But ringwoodite doesn't just store water, it actively drives our planet's living geology.
Water reduces the melting temperature of mantle rock, acting like an internal lubricant, allowing tectonic plates to slide smoothly.
Without hydrated ringwoodite in the transition zone, Earth's mantle would be too stiff and rigid for plate tectonics to exist. Plate tectonics recycles carbon dioxide, regulates global temperature, and creates oceans, continents, and mountain ranges.
Look at Venus or Mars. They have no active plate tectonics. Their mantle water was lost or never trapped, leaving them geologically dead. Ringwoodite is the unsung engine that keeps Earth dynamically active and hospitable for life.
We all learned about the atmospheric water cycle in school. Rain falls, rivers flow to oceans, and water evaporates.
But Earth actually operates a second, massive water cycle that operates over millions of years deep underground.
Subducting ocean plates carry water down into the mantle, where ringwoodite traps it for hundreds of millions of years.
Eventually, mantle plumes and volcanic eruptions push that water back up to the surface, returning it to our oceans.
If this deep water cycle ever stops balancing out, surface oceans could either dry up completely or drown the continents.
Our surface ocean levels have stayed remarkably stable for billions of years, thanks to this subterranean reservoir. The discovery of hydrated ringwoodite isn't just changing how we look at Earth, it's changing how we hunt for alien life. Astronomers used to search only for planets with liquid surface water on atmospheric radar.
Now, astrophysicists calculate whether exoplanets have mantle transition zones capable of storing interior oceans. A desert planet with 0 surface oceans could actually harbor massive water reserves locked inside high-pressure mantle rock.
Ringwoodite proves that habitability isn't just about how close a planet sits to its star, but what's locked deep inside its crust. The secrets hidden inside Earth's deepest mantle are giving us a blueprint to find living worlds across the galaxy. It turns out that it wasn't completely wrong about a journey to the center of the Earth.
The ocean isn't down there as liquid waves, but as a massive geological reservoir preserving life on our surface world.
What surprised you more? That water exists 400 miles deep, or that a diamond proved it was real?
Learning how our planet operates deep beneath our feet gives us a whole new appreciation for the ground we walk on.
Let me know your thoughts in the comments below.
Hit that like button if you learned something new today, subscribe for more deep Earth breakthroughs, and I'll see you in the next video.